A vector is nothing more than the following. It's a segment with both a direction and I'll use the word for you despicable me people. It has both a direction and a magnitude. Do we know what a magnitude is? Do you have any idea what that word means? That's why I didn't really want to use this thing, but I like to pander to my audience sometimes. Magnitude means length, in our sense. Size, length. In general, it means like size. But for us, we're talking about vectors or two-dimensional objects. For us, they'll be length for us. Okay, you'll talk about vectors in a more broad sense later on. But length. It has a direction and a length. I also notice I call it a segment because it starts and ends. On a plane, these things are going to look like rays. Do we remember what a ray is from back in way at the beginning of the year, Petey?
A line, a point, so there's a point on the other side of the line.
Yeah, it's like half a line. It has a starting point, an origin, and it goes on in a direction forever. These are going to look like drawn similarly. Vectors always, well, not always, I guess, but in our sense, they will end. They have a start and an end point. The starting point is called the head. It's called the tail of a vector. It's kind of weird, but where it starts is called the tail. And we represent that with a dot. The head of a vector is where the arrowhead is, and we represent with an arrowhead. Okay. So when we name vectors, we're talking about vectors in terms of what's called their components. In 2 dimensions, vectors have 2 components. What's called the x component and the y component. Well, that's almost an impossible word to read. This is supposed to be component. X component and y component. We think of these as like change. How does this vector from its tail to its head, from start to finish, how does it change in the x direction? How does it change in the y direction? Is these 2 things. So it's hopefully by using the word change, we're evoking terms and words that we use a lot with slope of a line. Change in x, change in y. It's similar, very, very, very similar type of thought process here. So we're trying to find the x components. How does it change from tail to head, from start to finish? In this case, it changes by the x component. I like to turn this basically into a triangle and find the x component by counting boxes. 1, 2, 3, 4, 5, 6, 7. This goes to the left. 7. In the x direction. And in the y direction, what should the y component be? What's the change in y here? From start to finish. How much higher or lower does it go? Up 3. So we're going to end up eventually describe these in terms of numbers here. So rather than using up 3 or left 7, what would be maybe a more algebraic appropriate way to describe these? What would the change in x being going to the left 7? What's a better way to describe it? Negative 7. And going up 3, well, positive 3. Once we know the components of the vector is easy, we just write them as a pair. To tell that this is a vector, not just a point, however, we use these kind of like greater than or less than symbol brackets. And we'll say the change in x is negative 7, change in y is 3. Is in component form this vector. This is saying go to the left 7, go up 3. Okay, so in this case, where does this vector on the right start? At what point? N. How'd you know it starts N and not say up here? Oh, the dot. The tail's here. the head is up here. So it starts at the tail and goes toward the head. So we start here and ends up here. So if I want to describe this vector in component form, I need to describe how does x change from the start to the finish, and how does y change from the start to the finish. So how does x change from n to o? It doesn't go anywhere left and right, so it's 0. How about up and down? How does it change? It goes up 6. So is that positive or negative? Up is positive. So vector NO is 0, 6. See how I describe that. Notice also, like rays, we describe vectors from tail to head, from start to finish. So we would not, the vector NO is different than the vector ON. Starting at N, NO implies from the way it's written that we're starting at N and ending at O. Not the other way around. A vector has a direction. So by changing the order, we change the direction of the vector, which changes the vector itself. So a vector is one object. In our class, we're going to look at collections of vectors. And we're going to talk about those in terms of what's called a matrix. For this course, we're going to think of a matrix as like a collection of vectors. And in particular, a matrix in general is an array of numbers collected. Oh, that's not what I use for collected. I don't know what I'm talking about. Array of numbers that are related to each other. An array. Well, we know what an array is. I've heard of the word array before. Someone last hour used it in terms of like science and like solar energy. And did anyone look at that? Like a group. Yep. Variety.
Like a variety of like different types that all work together.
Okay, they're of different types that all work together. Absolutely, we're on the right path there. Anyone ever heard of what a solar array? A solar panel array? No? Did anyone do solar energy for their Green Earth presentation thing? No.
Solar.
An array, specifically in this case, is like a grid. Think of this as a grid. A matrix looks like this. We generally write it inside of a big set of brackets. We'll put, and that has a bunch of entries in here. Like, I use numbers to try to keep this as easy as possible. How about 1, 0, 3, 4, 6, 5, negative 10, 0. That was too much like hundreds.
I know.
This would in this case be one example of a matrix. It's an array or a grid of numbers or what are called elements, entries in here. There are 1, 2, 3, 4, 5, 6, 7, 8 entries in this matrix. Another word for an entry is an element. Is an entry in a matrix. So if I use the word element, I'm talking about one of the possibly many numbers that are inside of a matrix. So in this case, an element, this 3 could be an element. Is one of these 8 elements in this matrix. We can talk about the dimension or the size of a matrix. The dimensions of a matrix are described as two numbers. It's the rows by the columns. Rows go laterally, left and right. So here would be one row in this matrix. Columns go vertically. Rows by columns. In general, it's a number by another number, n by n is how we represent it. Be a row by a column. It's always two numbers. So in this case, the dimension of this example matrix I just drew up is a 1, 2, 2 rows by 1, 2, 3, 4 columns. This would be what's called a 2 by 4 matrix. The dimensions are kind of important as we go through, just as far as knowing what we can do with the matrices, what we can do with these matrices. But in general, we'll have rows and columns. This would be a 2 by 4. What's nice is that since we're thinking of these matrices as just collections of vectors, we can actually represent entire geometric objects on a plane by a single matrix, as opposed to a ton of different vectors added together or a collection of points. We can actually keep them very organized as a matrix. So what we're going to do to represent objects on a plane as a matrix, we're going to represent them as a vector, and more specifically, a column vector, or a vector written vertically, up and down. So if I want to represent any of these, I'm going to look at the points and try to figure out what vector gets me to each of these points. So for example, I want to get to point T, which is supposed to be up here. What vector takes me from the origin to point T? How would I move what vector, how to describe this vector that takes me from the origin to point T? 3, and then this is up like in the middle of this box, and this is a kind of a confusing diagram because vertically we're counting by 2s. So yeah, this is actually 2, 4, 5. So 3, 5. This vector that takes me there can be written as 3, 5. As a matrix, it's easier to manipulate this thing if we write what's called a column vector. So we're going to take this and write it vertically. X on top, Y on bottom. So this matrix is maybe more appropriately, the matrix that represents point T would just be this vector written as a column. Take this XY and flip it so that the X on top, the Y is on bottom. You'll understand why I want you to do this in a second. Okay. The Y will be very apparent when we start manipulating the matrices together. Y, it will make sense. You have to go on faith for a little second. By convention, we're going to write this matrix as a column vector. So all I did was find what vector takes me from the origin to the point, and I'll write that as a column vector instead of a row vector. I guess you call that. So if I want to represent this whole quadrilateral, W, V, U, T, as a matrix, I can represent it as a collection of these column vectors. So if I can write the column vector for W, for V, for U, and for T, I can collect them as one big matrix. So like, what would the column vector that represents the W? How would I go, what vector takes me from the origin to point W? This is supposed to be W. This is supposed to be W, this is supposed to be V, this is supposed to be U. So like, what vector takes me from the origin to W? I go back 2 and up 1. So -2, up 1 takes me to W. What vector takes me from the origin to V? Back 1, down 2, 4, 6. So as a column, that's down 1, back 1, down 6. What vector takes me to U?
4, 2.
Over 4, down 2. And then what vector takes me to what we've already found? What vector takes me to T? 3, 5. So this quadrilateral can be represented by this matrix instead. So rather than needing this diagram, we can actually think of this in terms of just its points. This collection of points written vertically represents this quadrilateral, W, V, U, T. Just a quick refresher, what's the dimension of that matrix? What's the dimension of the matrix that represents W, V, U, T? 2 by 4. Okay. In particular, we can do the two common representation. The two common operations we do is addition and combine with subtraction and multiplication. If I want to perform what's called matrix addition, if two matrices have the same dimension, they have to have the same dimensions, then you can add or subtract them by adding or subtracting them element by element. If I want to add two matrices, first of all, they have to be the same size. If they're not the exact same size, don't even bother. You can't do it. It doesn't make any sense. So once you've determined that they are, you can add them, then we'll add them or subtract them element by element. So I'll take, say, in our example here, I want to add this 2 by 2 by this 2 by 2. They're the same size, so we're allowed to add them. And if I want to add them, I'll add them element by element. So I'll take the first element, the first element in first row, first column, and add it to the element in the first row, first column of the second matrix. So this would be 7 plus -8 will give me the first element, the element in the first row, first column of my sum. I'll take the first row, second element, and add it to the first row, second column of the second matrix. 2 plus 1. Row 2, column 1, row 2, column 1. -5 plus 4, 9 plus 0. And then simplify these. Seven plus -8 gives me -1, 3, -1, 9 would be the matrix addition of these two. Element by element. Row 1, column 1. Row 1, column 2. Row 2, column 1. Row 2, column 2. The same thing applies to subtraction. Just subtract in element by element. Let's get this example on your own real quick.
Oh my gosh, these notes are
Just say it.
Yes.
Why does anybody actually watching? This is secretly I love when when are we almost done?
Yeah, that's the last.
Oh, we're just talking about burgers.
Matrix multiplication is different than matrix addition. We are not, and I repeat, not going to just multiply term by term. This is not how matrix multiplication works. Okay? Matrix multiplication is a little more complicated. It's not terribly hard. It's just different. Okay? I'm going to start by doing it. I'm going to start by running an example, by working an example, and then we'll write down what the actual steps are, so we kind of have a more concrete way of looking at it. when we multiply two matrices together, we're going to multiply a row in the first matrix by a column in the second. We'll figure out how to do that. For example, in my answer to this matrix multiplication problem, if I want to figure out what the element in the first row, first column of my answer, I'm going to multiply the first row by the first column of my two matrices. Oh wow, how do we do that? I'm going to multiply those two things together. How do I do that? I'm going to tell you the scientific way of how I do this. I'm actually currently taking a class right now at Eastern Michigan about what's called linear algebra, which is this stuff but at a higher level. What I do, and this is very scientific, I take my hand, my fingers. I even do kind of do like the Hawaii surfing thing with the thumb and pinky, and I go column to row, column to row. So it tells me what I'm multiplying together. So I'm going to multiply them element by element and then add together. This is more technically, this is called a dot product. What we're doing is taking first elements, multiply together. Second elements, and multiply them together, and add together. This is called what's called a dot product. Okay. So in this case, I'm going to take 3 times 2, negative 5 times 0, and add them together. This will give me the element that's in the first row, first column of my answer.
Oh, so it's the one that overlaps.
Yes. So to get the answer in the first spot, row 1, column 1, I'll take row 1 and multiply it by column 1. So if I want to get the answer that goes in row 1, column 2, I'll take row 1 and multiply it by column 2. Column 2.
Then do you multiply negative 5 by 6 and negative 1 by 3?
So then for the second entry, I'll take 3 times negative 1 and take negative 5 times 6 and add those two answers together. That'll give me the entry in row 1, column 2.
Oh.
Row 1, column 2. Is the procedure for matrix multiplication. So then if I want row 2, column 1, I'll multiply from my matrices, I'll multiply row 2 by column 1. So I'll get 1 times 2 and add that with 4 times 0. Row 2, column 1. Row 2, column 1. And if I want row 2, column 2, then I'll finish it off by row 2, column 2. 1 times negative 1, 4 times 6. Simplify these things and you get 1, 2, 3, 4 entries. So we get 3 times 2 is 6. 6 plus 0. I'm going to erase these and put the actual answer. 3 times 2 is 6. 6 plus 0 is 6. 3 times negative 1 is negative 3 plus negative 30 gives you negative 33. 1 times 2 is 2. 2 plus 0 is just 2. Negative 1 plus 24 is positive 23. The multiplication of these two matrices together gives the 2 by 2, 6, negative 33, 2, 23. Let's think. We're going to create a new matrix by multiplying a row from the first matrix by columns in the second. Okay. And multiplying specifically, the technical term is called a dot product. You do not need to know that. That's not important at this point. You'll cover that later, a little bit in Algebra 2, and certainly if you move on to take pre-calculus and calculus further down the line. Knowing that's a dot product is not necessary for this course. But wait. We're going to create our new matrix by multiplying rows in the first by columns in the second, or dot product. Rows in the first by columns in the second. And that will give you the corresponding element, row by column. Let's try it again with this, another set of 2x2s here. So, let's see, I'm going to take, to get row 1, column 1, I'll multiply row 1, column 1. So this matrix should be, I'm going to skip the step where I had explicitly what numbers are being multiplied together. I'm going to multiply them together in my head. So I'll have the addition of them, but I'm going to skip that first step. So I have 1 times 3 is 3. 0 times negative 4 is 0. Is row 1, column 1. Row 1, column 2, I'll get by multiplying row 1, column 2. So 1 times 8 is 8. 0 times 7 is 0. Okay, there's no more columns, so I'll go to the next row. Row 2, column 1. Row 2, column 1. 0 times 3 is 0. Negative 1 times negative 4 is positive 4. Row 2, column 2. Row 2, column 2. 0 times 8 is 0. Negative 1 times 7 is negative 7. Combine those things together, and you get a new matrix by the multiplication method. So we should get the matrix, your answer should be what? 3, 8, 4, negative 7. These two are very important examples. Let's see what kind of matrix we get when we multiply these. Notice that these two matrices don't have the same dimension. Unlike these two, they are both square, they're both the same. These two have different dimensions. So let's follow our multiplying rules and see what we get as an answer. And maybe we'll drive that last box that says, what are you allowed to multiply together? First of all, I would like you to let's describe what the dimensions of this are first, and then we'll think about what the answer is going to be. What's the dimensions of this first matrix?
1 by 2.
1 row, 2 columns. Okay, what's the dimensions of our second matrix? 2 rows, 1 column. All right, let's try to multiply these things. So let's see. My first entry, I get for the first row, first column. So my first entry in this matrix should be what? 5 times negative 3 is negative 15. Plus 1 times negative 2 is negative 2. So my first entry in this matrix is going to be negative 17. What's our next entry going to be? There is no other entry. This is a matrix with 1 element. What's the size of that matrix? This is a 1 by 1 matrix. All right. Let's contrast it with our second example. This is similarly, this is a 2 by 1. And this is a 1 by 2. Let's multiply these. I'm going to get the first row, first column. First row, first column by getting, let's see, negative 3 times 2 is -6. Are there any other entries we can get? I hope there are. There's a bunch of numbers we haven't multiplied together yet. A lot of combinations. How about the first row, second column?
Wait.
Yeah, you'll have the number of rows in the first matrix by the number of columns in the second. Will be your final. Will be the size of your final answer. And so conversely, the number of columns in the first must match the number of rows in the second. Yes. There were 2 more examples. You can finish them out. This will be a 2 by 2. This is just a 1 by 1.